Perfection. My most elegant design, a veritable monument to electronic inspiration.
Hey Bob, that new 1230 logic analyzer came with an operations video. Thought you'd like to see it.
Oh yeah, thanks Doug. I'll get to it right away. Project completed hours ahead of time. I begin my vacation tomorrow. First I've had in years. Why, everything's wrapped up here. I could leave now. But wait, why not stick around and accept their congratulations in person? They'll take the first production boards, test them, and bingo! First time, every time, perfection. I wonder what Al will say. Maybe a bonus, maybe a promotion. I can just see his smiling face now. Al?
But Al, you don't understand. I've done my job. I leave for the islands tomorrow at 7 a.m. I need this vacation.
Gee, that's too bad. Because you're not leaving this building until manufacturing can produce the product.
That could take weeks.
Yeah, months even. Good thing you got the rest of the day.
Traitor.
So much for establishing blame. I steadied myself and tried to review the problem. Good data was coming in, but nothing was coming out. The board's main function was to handle input data. The circuit in question took the data through a series of latches before storing it in RAM, or at least that was my plan. Somehow, the board was drowning the data before it got to the RAM. I had two questions: where and why? And I had to find out fast or my dream vacation would disappear with the data. I'd have to find where before I could determine why. I resolved to start at the first latch and then slog my way to the RAM. Of course, there were 8 to 16 data lines to check at each location, not to mention address and control buses to chase. I could probe each line location by location with a scope, or
I could learn to use the 1230. Gee, I hope it's in color.
It had seemed easy in the videotape. Triggering, channel groupings, time base, timing diagrams, and state tables. I'd never used a logic analyzer before, but the 1230 seemed to be both versatile and fairly obvious to use. It was laid out like an avant-garde oscilloscope, a large CRT on the left with probe connectors and a keypad on the right. There wasn't a control knob or a BNC in sight. A few things from the videotape came back to me, like it being a good idea to plug probes into the 1230 with the power off, but to be sure I turned it on before I connected the probes to the system under test.
And that the power switch is on the back left.
It greeted me with the date and time and suggested I use the menu key to continue. I could see that the keypad had several distinct sections. Its left-hand side was data entry. A box on the top held start and stop keys, while the cursor arrow surrounded an enter key. Finally, menu was nestled just above the connectors between notes and don't care. The main menu was kind of fascinating. It let me access all the different setup, display, and utility menus. I could select a menu with a cursor and press enter. Or I could press the assigned data key. And I could return just by pressing menu.
Cute, but let's see how you really work.
I attached a dip clip to the input of the first latch and patched on 8 of the probe's color-coded lines.
Let's see, to be sure if there's any data on the lines, I'll trigger asynchronously.
As if reading my mind, the default menu was time base. I pressed enter to call it up. Async, the internal clock, was already selected, but its 1 microsecond rate would be too slow. My fastest data would be coming in around 600 nanoseconds or so. I realized I'd need to sample at a faster rate to see transitions, maybe a 400 nanoseconds. But how? The message bar at the bottom of the screen explained what to do. I cursored into the rate field and then used the 0 and 2 keys to select 400 nanoseconds.
Now what? Well, the video said I could just press start and... All right!
So this was a timing diagram. It looked a little like an oscilloscope display with a lot of extra traces. The left-hand column displayed trace names, while the far right-hand column zeros and ones changed as I moved the cursor. The top showed straight lines.
Oh, those must be the 8 probe lines I haven't attached yet.
While below, there were some unbelievably square waves. Then I remembered. Ringing and overshoot were a scope's domain. The logic analyzer cared only which side of a voltage threshold the signal was. When the signal was below the threshold, that was a logical 0. When the signal was above the threshold, a logical 1. And the right-hand column simply read the cursor position as 1s and 0s. And those 1s and 0s made up the data word at that moment in time. The message bar explained how to move around in the display memory. The cursor left and right moved me gently, while up and down took giant strides. And the strides could be lengthened or shortened by one of the many special functions summoned and described by the F key. At the top of the screen, a memory bar kept me up to date on my location in the 2K memory sample and my relationship to the trigger point. Thrills and chills aside, I now knew 2 things. 1, the fact that I had data on all 8 lines meant my signal was good going into the latch.
And 2, I'm actually using a logic analyzer. Now, how can I use this tool to find if anything's going through the latch?
Well, I patched the other 8 lines to the other side of the latch and repeated the test.
What?
The top half of the screen should have looked a lot like the bottom, but all I had was the same 8 lines of incoming data and nothing coming out. I reviewed the possibilities. Bad ICs? But every one of the production boards had failed. Now, either something dramatic was happening during insertion or... Hurriedly, I tore channel 15 loose and attached it to the latch's system clock. When I repeated the test, I found that the outputs of the latch weren't moving, and neither was my clock.
Could it be that simple? A grounded clock line?
Logically, it made sense. If the latch never received a clock, it could never pass data through. Since I knew what to look for, it took only seconds to find a flaw in the solder mask. I cut the flash away and tried it again.
Gotcha!
Data on the output channels. I could almost hear the breakers hitting the beach. Or was it Al hitting the ceiling if I'd missed anything? The real problem was not whether I got a signal through the latch, but whether the board would pass final test. Had I checked the RAM? No. Had I checked to see if the data was correct? No. Was there more I could do?
Yes, because I have the rest of the day and at 12:30.
The little asterisk by the setup title reminded me of the changes I'd made. I decided to save this test configuration before I got fancy. How had they done that on the video? Right. The menu key brought back the main menu, and B called the storage menu. Default was hardly memorable, but the message bar showed me how to change it. I moved the cursor down and off to enter the name field. I pressed Enter, and then held the up or down cursor key until an M. I entered it with a right arrow. The A I selected directly from the hex keypad. I added a U and an I and covered the last letters with don't care blanks. I punched 2 to save the setup and name. The 1230 asked me if I really wanted to overwrite the previous setup. Pressing enter again told it I did. Then I pulled out my schematics and considered the problems. I had acquired a new tool with the 1230 and had barely tapped its power. Besides, I'd already accomplished a few days' work and it wasn't even time yet for coffee. So I traced out the data flow and selected logical areas to probe. The video had really been only a primer, but the 1230's user interface kept things moving along easily. My last test was the RAM itself. I was reaching for the suntan oil when it happened. One memory data line refused to change. My entire corporate life passed before me and ended on a fat cigar. It was an appropriate time to panic. Or was it? I knew from previous tests that all of the data lines were toggling on the other latches, but that didn't mean this line had to toggle on this screen. It could change states just off screen or a million miles down. I might have to scroll for a long time to be sure, or I could take advantage of some 1230 features. I used the F key to quickly change its resolution. Now I could see the entire 2K sample and the line stayed low. But I still wasn't convinced. I wanted to search even further, painlessly. I'd changed the 1230 trigger spec to search way beyond any 2K sample. My plan was to trigger on the line going high. The 1230 would scan the data for that condition until that change occurred, or I stopped the test. If I can figure out how to do it. Then I remembered the videotape. It said to change things systematically by running through the main menus in order. Time base, then channel group, trigger spec, conditions, and finally run control. Because a change in one sometimes required changes in the menus that followed. Take time base, for example. Time base shows whether an internal asynchronous or an external synchronous clock was selected. The clock rate, whether I wanted to capture signal changes or glitches between regular samples, and the threshold setting for the probes. But all I wanted was to be sure I had a fast enough clock to trigger on any data. Asynchronous 400 nanoseconds. Perfect. Pressing menu again, I selected 1, channel group, which controls how data lines are named and displayed. The default name seemed adequate, so I moved the cursor to radix to change the number display format from hexadecimal to binary. The plus sign under polarity just meant the line was logically true when it went positive. Channel definition showed the arrangement of channels in the group. I had them in descending order, channel 15 to channel 0. Looks okay to me. Next, I punched up trigger spec, short for trigger specifications. This menu defined when the 1230 would trigger. If A happens once, then trigger and fill memory. A window at the bottom conveniently displayed the current value or definition of whatever field the cursor was on. In this case, A, all don't cares. The trigger setup was fine. All I needed to alter was the trigger condition, which I could do by selecting the Conditions menu. My first option was to change the condition name or symbol. I wanted something that would make this test self-documenting. I renamed A Bob. Then I moved to the suspect line and changed its don't care to 1. That means high. In other words, the 1230 would ignore the other lines and trigger only if this line went high. One more step, run control, menu and 4. It opened up a whole new world. Now I could select which of the 1230's 4 memories to use. The format of the display, where the trigger would be located in memory, when the 1230 would look for a trigger, memory comparison specs, and lots more. Then I reran the test, or tried to. Only if a logic high appeared on the line with the 1230 trigger. After a couple million clock pulses, I stopped the acquisition. The line was still lying down on the job, which seemed rather familiar. So for documentation, I labeled the line Al. Now I've got to find what's keeping her down, Al. I shut off the system and visually traced the line to the fault. Solder mask again. A tiny but fatal bridge had grounded my memory data line. As I replaced the board and powered up the system, I wondered what other flaws might be hidden. Until now, I'd kept my tests very simple. Either it was there or it wasn't. What if a problem were more subtle? What if the data was there but garbled? Would our tests prove that the data was correct? Could I know, for example, if the data was getting from the first latch to the memory without damage? I could, but I'd have to work a different side of the 1230. Logic analyzers are really samplers. They report whether the line is high or low at each clock pulse, or sample. The asynchronous sample rate determines the resolution of the display. The faster the sample rate, the higher the resolution. Logic analyzers that rely on asynchronous sampling are called timing analyzers. But to compare the data before and after the latch, I only wanted to see what happened when the words were valid, and that meant when the system's own clock pulsed. Logic analyzers that use the system clock for sampling are called state analyzers. Fortunately, the 1230 was both a timing and a state analyzer. This time, I'd patch 8 of the probe's channels to the outputs of the first latch, but attach the other 8 channels to the memory's inputs. Then I set up a count pattern as the stimulus. If the circuit was functioning correctly, the data should be delayed for 2 clock pulses, but not otherwise changed. But I needed to sample synchronously to determine that.
Now, how did they do that on the videotape?
Well, it would help if the 1230 were connected to the system clock. I connected one of the probe's clock lines to the latch's system clock. I knew from the schematic that the system under test used a rising edge. I decided to run through their checklist for changing setups again. I called up the time base menu. The message bar sent me to the 0 and 2 keys and up popped sync. Channel groups and trigger spec were okay, but I changed the trigger condition to be all zeros on the output of the first latch. That way, I'd be sure to trigger on the start of the count. Feeling a little like a pioneer, I press start.
Hi-ho, trigger!
The count pattern showed up as expected on both the latch and the memory. But was it delayed by exactly 2 clocks? I pressed enter to set a reference at the trigger, then I moved the cursor from the start of the count on the latch to the start of the count on the memory. The reference to cursor readout showed me what I needed to see. The counts were skewed by 2 clock cycles.
Okay, let's take a look at state here.
I pressed menu and 7 and selected the state display. At first glance, the state format seems very different from the oscilloscope-like timing display. But it's really just a slightly but importantly changed perspective of the same information. Imagine a timing display. Now, rotate it 90 degrees. The old x-axis of the timing display becomes a y-axis. And now it shows time as successive memory locations. The timing display had y-axes, data channels, and the cursor word. These become the state display's x-axis, with the channels organized as groups. The root information in each display is the same. I knew my clock pattern was still there. To see what the pattern would look like in hex format, I used one of the state table's options to change the radix to hex without leaving the display. There was the start of the count on the latch. And there's the start of the count at the memory. The 2 clock pulse lag was especially easy to see on the state table. There were 2 samples of each count because the clock on the system was twice as fast as the data rate.
Wonderful!
It struck me that the more I learned about the 1230, the more uses I had for it. So far, all I'd tried was troubleshooting, but the videotape had touched on many more applications. For example, analyzers are great for testing pieces of circuits as they are developed. Now, I could have verified my hardware to see if changes were correct, or even necessary. And I would have had fewer board turns if I had used the 1230 to find and document faults. And I could even have reduced firmware delays with an optional disassembly probe by tracing how hardware and software changes affected the system. And I could have saved documentation time by using the optional printer port or a video copier to make visual records of the process, or even develop procedures for production test.
Ow.
And I had an immediate need for a good production test, one that would verify that the solder masks were correctly aligned. I could load manufacturing's 1230 with canned setups and good data for comparisons. That way, I could leave, sure that all the problems were solved, and sure that Al wouldn't pursue me all the way to the beach. The compare function was one of the many covered in the videotape. Since Tektronix had given the 1234 non-volatile memories for data logging, I could load up a memory with the data from a known good board and then compare it to a board under test. As I got into less familiar territory like run control, I made good use of the notes key, which described how to use each menu. With its help, I saw that I wanted to send the next test to, say, memory 2. Then I pressed Start again to load reference data from the board I'd corrected. Yes, the familiar stair-step was there. I also plugged a video copier into the composite video port and back and recorded the screen for documentation. Then I re-entered the Run Control menu and changed the update memory back to 1. And now I could rerun the test without overwriting my known good comparison data. Next, I changed the display to State. This meant that the 1230 would automatically display the state table when it triggered instead of the timing diagram. Then I set it to compare the new data in memory 1 to my known good data in memory 2. And that brought me to the question of masking. In a comparison, any channel specified as X or don't care would be masked or omitted from the comparison. I needed to compare all 16 channels. But the currently selected mask condition was Bob, and I could see in the viewport at the bottom of the screen that Bob had don't cares for the upper 8 bits. I'd need to create a different condition for the channel mask. I accessed the Conditions menu and set up another condition named No Mask, with all 16 bits set to 1. That way no channels would be masked. Every one would be compared. I explained the faults to production, and while they were repairing the old boards and realigning the solder mask, I filled my comparison memory with data from a board I knew was good. By using the same stimulus in the 1230, I could exactly repeat the test on the new boards. If there were any differences now, I'd know the repairs were not complete. But if the 1230 found no differences, my next board would be on the surf. I attached the first repaired board into the test fixture, scanned the waves, and pressed Start. So far, so good. I pressed C to begin the compare function. If there were any differences in the two memories, they'd be highlighted on the screen. Cowabunga! A perfect run. The comparison found no differences. The data from the new board was the same as the data from the known good board. Now, with this new setup and test, it would be easy for production to test the next batch of boards. I promised them some postcards and headed back for my bench. As I packed, the day's events passed in review. After all, I'd gained a major productivity tool and saved Big Al's production schedule simultaneously. With a little help, I'd learned how to connect probes, access menus, start and stop acquisitions, use asynchronous and synchronous clocks, change channel groups, specify a trigger, name and enter condition words, save setups, scroll data and change resolution in the timing diagram, change display radix in the state table, use the notes key, compare one memory to another, make screen copies, and change the setup systematically from one test to another. Not a bad beginning. Now it was time for a little creative thought.
Well,
Bad news.
bad news.
3 weeks.
3 weeks?
Yeah. You won't see me here for 3 weeks instead of 2.
You, me, see, 3? What?
I checked her schedule. I'm already a week ahead of it. Here's the documentation. Nice pictures, huh? Turns out the 1230 can do almost anything.
Aloha!
Don't get the idea that I was a hotshot just from watching a videotape. All the tape did was illustrate some basics. But the 1230 invites you to become an expert. Its easy-to-learn interface and built-in helps lets you concentrate on concepts instead of idiosyncrasies. It features a good manual, a well-laid-out workbook, and even a test circuit for practice. Now I needed just a little more time to learn all of its capabilities. A little time like on the plane.
Hey, don't sweat it. You can fly for half price.